Welcome back. Today we're going to be talking about just different ways to compute probability. In particular, we're going to be looking at the addition and multiplication rules for probability. These are just different ways to kind of make it easier when we're trying to actually make these computations. So the first thing we want to talk about is just a couple properties. So one property is if you have an event, the probability of that event taking place needs to be between 0 and 1. Now 0 would be 0%, 1 would be 100%. So if I say what's the probability of rolling an even on a die, that probability has to be between 0% and 100%. If it's an event, it needs to come from the sample space, and it doesn't make sense for me to have a less than 0% chance. What is a negative chance in probability? And it also doesn't mean to have 120% chance. Not only do I roll an even, I rolled it like twice in the same roll. That doesn't make any sense. So it has to be between 0 and 1, or 0 and 100%. So for instance, rolling an even on a die has a probability of 50%. And I did it. Great, I win. Another property is that for any sample space, the probability of that sample space is 1. Now the sample space is the list of all possible outcomes. So when I'm looking at a die, the probability of rolling anything is 100%. So it seems weird, but what I mean here is that if I look at rolling a die, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. The probability that I roll one of those things when I roll a die needs to be 100%. What is the probability that when I roll this die, it lands on 1, 2, 3, 4, 5, or 6? 100%. Look, I rolled a 3. It's a 1, 2, 3, 4, 5, or 6. Great, it's 100%. For the empty set, the probability that that happens is 0. Now this seems really strange that we would even bring this up. But the empty set is that I roll and nothing happens. Well, something does happen. I rolled a 1. What's the probability that I didn't roll something on the list of 1, 2, 3, 4, 5, or 6 when I rolled? There is a 0% chance that that occurs. Before moving on to some of the other things, I want to talk about two specific examples that come up a lot in probability. One is rolling 2 dice. When you're rolling 2 dice, here I've got a green die and a red die. When I roll these 2 dice, what I'm looking for is the possible things that we could roll. So I could roll a 1 on the red die and a 1 on the green die, and that happens to be this one right up here in the corner. I could roll a 2 on the red die and a 1 on the green die, and that's the next one. And if I keep on doing this by looking at the different things that could happen on the red die and the different things that could happen on the green die, all the possible outcomes show up on this grid, the 6x6 grid. There are 36 different outcomes in this sample space. Now, this chart is a sample space for rolling 2 dice. It tells me every possible outcome. It is a list of every possible thing that can occur. And from it, I can start to compute probabilities. So for example, I could say, what is the probability that I get a sum of 6 when I add up the 2 dice that I roll? And what I would do using the stuff from last time is I would count the number of outcomes that have a sum of 6. So let me kind of erase that. And let's look at those outcomes. I could land on 1 and 5. I could do 2 and 4. I could do 3 and 3, 4 and 2, or 5 and 1. There are 5 different ways to roll a sum of 6, and there are 36 ways to roll the 2 dice. So the probability that I get a sum of 6 is 5 out of 36. Notice that that's between 0 and 1, so that works out for our properties of probability. And it's a good way for me to compute the probability when I'm rolling 2 dice. There are other probabilities I can do here. Since I have the entire sample space, I can really get a good feeling for what I'm supposed to get. The second type of probability that will come up a lot involves decks of cards. So when I talk about having a deck of cards, I want it understood what I'm talking about. A deck of cards is a deck of 52 cards Those 52 cards have different things on them, and you can kind of see some of them on the screen here. You could have a king of clubs. Notice that the value for this card is called king. The suit for this king is clubs. It's that black symbol next to the K. And there are different cards. Each card has a value and a suit. So this is a 3 of diamonds. This is a 10 of hearts. This is a 10 of diamonds, a 10 of spades. And what ends up happening is there are 52 cards because there are 13 different values. Those values are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then some weird ones, jack, queen, and king, which you saw just a minute ago. There are also 4 suits, diamonds, hearts, spades, and clubs. And if you take 4 times 13, you get 52, because there are 52 cards in a deck. The diamonds and the hearts are red, the spades and the clubs are black. So when I'm talking about probability in a deck of cards, I could say something like, what is the probability that I get a heart? Well, if I draw a random card, what's the probability that I get a heart? So the outcomes in this sample space would be each individual card, and there are 13 hearts, so the probability that I get a heart at random is 13 out of 52, or 1 out of 4. Nope. I could try again. And about 1 out of every 4 times I should get a heart. Yep. Nope. Nope. So I got 1 time out of 4 times. Now, is that going to happen every single time? No. But about 1 out of every 4 times, if I keep on doing this over and over and over again, which I'm not going to bore you by doing that, I should get a heart. So, now that we've talked about some different types of experiments, let's talk about the complement of an event. The complement of an event is denoted E with a C just to the upper right. It's a superscript. Is a set of all outcomes that are in the sample space that are not in E. And there's a complement rule that says if I take the probability of the event plus the probability of its complement, I get 1. So let's talk about dice. So if I roll 1 die, my possible rolls in my sample space are 1, 2, 3, 4, 5, and 6. So if the event is roll an odd, then the complement of rolling an odd is that I've rolled an even. Now why is that true? That's because roll an odd means I roll a 1, a 3, or a 5. And the things that are left in the sample space that are not in my event E are the evens, 2, 4, and 6. Now, the probability that I roll an odd is 3 out of 6. And the probability that I roll an even, for the complement, is also 3 out of 6. And if I add those up, I get 6 out of 6, which is equal to 1. This is really nice because if you are able to compute the complement of the event more easily, then you could compute the complement and know that the actual event probability is just 1 minus the probability of the complement. So the complement of event, this property is a pretty nice property to have. Another rule that's pretty nice is called the addition rule. And that is if I want to take the probability of one event or the other event occurring, then I could add those probabilities together, but then I have to subtract the overlap. If the events are mutually exclusive, meaning that there's no overlap, then you can just add the probabilities together. So I want to do an example of this, and you can kind of see how this works out. And one of the things I want to note is that in these videos that are about 15 minutes long, I'm going to do examples that serve for a way to show you how these rules work out. You cannot expect that I can show you every possible example in a 15-minute video. So really, I'm just trying to give you an idea as to how the rule works, but it's going to look way different in any scenario that's not the one that I'm showing you right now. So for example, I could say, what is the probability if I choose a card, so I got my 52 card deck, what is the probability that I get a club or a 7? Now the addition rule says I'm going to take the probability of getting a club. So maybe I'll draw a club. And I'm going to add it to the probability of getting a 7. And then I'm going to subtract the probability of getting a club and a 7. Well, the probability of getting a club is similar to the probability of getting a heart from earlier. There are 13 clubs, and there are 52 cards. So in this experiment, I'm just drawing one card. The probability of getting a 7, there are 4 different 7s. 7s of hearts, 7 of clubs, 7 of diamonds, and 7 of spades. So there's 4 out of 52. But then I'm going to subtract the probability of getting something that is a club and a 7, the overlap in the event. The reason why is that if I pulled out every card right now that satisfies club or 7, I would have 13 clubs, and in that pile I'd also have 4 7s. But there's one card that actually satisfies both, and that's the 7 of clubs. So the probability of getting a 7 and a club is 1 out of 52. There's only one card that satisfies that. Now sometimes there are lots of things that satisfy that E and F, but in this case it's just one card that is both a 7 and a club. So if I take 13 plus 4, I get 17, subtract 1, I get 16, so the probability that this happens is 16 out of 52. It's a little bit better than a quarter, so let's see if it happens. Club or 7. Ace of clubs satisfies the what I wanted, but it's not always going to happen, or maybe it will. So jack of clubs. There we go, 10 of spades. It's going to happen a little bit more than 1 out of every 4 times. Now, if the events are mutually exclusive, you can just add them. So if I said, what's the probability of getting a club or a spade? It'd be 13 out of 52 plus 13 out of 52. There's no overlap. There's no card that's both a club and a spade. I could have bigger overlap. I could say, what's the probability that I get a club or an odd number, right? Then the overlap there, it would be an ace of clubs, a 3 of clubs, a 5 of clubs, a 7 of clubs, and a 9 of clubs. There'd be 5 cards that overlap, so I'd be subtracting something bigger. Just kind of depends on what your overlap is between those two events. And if you want to see what the overlap is, a lot of times you could just write out all the cards that satisfy, and you can kind of start to see that overlap. The second rule I want to talk about here is the multiplication rules. And in order to do that, I got to talk about independent events and dependent events. So independent events are events that they don't depend on each other. Here's a good example. Say I roll the green die, and then I roll the red die. These are independent events because after I roll the green die, the red die does not look at the green die, see what it rolled, and then change its mind on what it's going to roll. That would just be creepy. It's just not going to happen. So these are independent events. Dependent events would be something like I draw a card, I set that card aside, and then I draw another card. Now these are dependent events because whatever that first card is cannot be drawn the second time. Therefore, when I'm trying to make a computation, I have to pay attention to the fact that the second event depends on the first. When you use the multiplication rule, you're trying to find out the probability that two things take place simultaneously. So for example, what is the probability that I roll an odd on the red and on the green I roll a larger than 3? Well, in order to compute that probability, what I'm going to do is I'm going to take the probability that I roll an odd, which is 3 out of 6, so probability that I roll an odd, and I get 3 out of 6, and I multiply that by the probability that I roll larger than 3. So greater than 3. Well, that means I have to roll 4, 5, or 6. That's also 3 out of 6. 3 out of 6, and so I get 9 out of 36. Not a bad odds. So now I'm going to roll those two dice. We'll take a look and see what happens. I'm hoping for an odd on the red and larger than 3 on the green. Odd on the red, so that worked out. but a 1 on the green, so that did not work out. Odd on the red, so that's a 1. Larger than 3 on the green, so that worked out. Even on the red, didn't work out. Odd on the red, larger than 3 on the green. Right, so I'm multiplying those two probabilities because in order for it to work out, both the red has to satisfy it and the green has to satisfy it. And these are independent events. The second one is two dependent events. So here's an example of dependent events. What is the probability that I pull a club without replacing the card, then I pull another club? So what's probably like a club followed by a club? According to this rule, the multiplication rule says that is the probability that I get a club multiplied by, and this is a conditional probability. This is the probability of E given that F occurs. So in other words, what is the probability that I get a club and then another club? It is the probability that I get a club multiplied by the probability that I get a club assuming or given that I already get a club on the first one. Given that the first card is a club. So this is equal to, the probability I get a club on the first card is 13 out of 52. But then here's the strange thing. The probability I get a club given that the first card is a club. If the first card is a club, I now have 52 cards, so I've taken a club out. I now have 51 cards left in the deck, and only 12 of them are clubs. And so I've got to multiply by what this is a conditional probability in order to actually get this. And so when I multiply those two numbers together, that gives me the probability of these two events taking place. That conditional probability comes in because these are dependent events. The probability I club the second time is going to be dependent on the fact that I got a club the first time. And so I'm going to have one less club in the deck. I'm going to have one less card in the deck. And so that's why I'm going to multiply by that. All right, so when I'm talking about probability, I can kind of put all these rules together and start to compute things. So I want to do one more. And that is, what is the probability that I pull two cards from the deck and both times? And what is the probability that if I pull two cards from the deck, at least one is a club? And I'm going to use some of the rules that I've got. So probability of at least one club. And here's what I'm going to do. I'm going to kind of show you how to work this problem out. Getting at least one club when I pull two cards from the deck is the opposite, the complement of not getting a club at all. So if I use that, the complement of this, so if this is my event, then E complement is equal to not getting a club. The reason I bring this up is because it's actually easier to take the probability of not getting a club. Now remember that if I add up the probability of getting a club and its complement, it should add up to 1. That means that 1 minus the probability of no club would be equal to the probability of at least one club. So now, what's the probability of not getting a club? Well, I can use the multiplication rule. So the multiplication rule would say it's the probability of not getting a club the first time and not getting a club the second time. These are dependent events because I'm pulling two cards out of the deck. So I'm going to take the probability of not getting a club the first time, which would be, well, that would be 39 out of 52 because there are 39 cards that are not clubs. Then I multiply by the probability that I don't get a club again, assuming I didn't get a club the first time. There will be 38 less non-club cards, 51 less cards in the deck. Now if I multiply those two numbers together, subtract it from 1, this is the number that I'd be going for as my probability. So this is just a couple different rules you can use when you're trying to figure out some of these probability things.